All right. Hi, everyone. I'm Howard. If you don't know me, I'm a co-founder of Aleo, and today I want to talk a little bit about programming in zero knowledge and the programming model of zero knowledge. I think there's been a lot of discussion, especially over the past few years, about building out ZK virtual machines, and especially in light of the discussions recently with ZK EVMs, I thought it would be worthwhile and a good use of this opportunity to really talk about the challenges with respect to the account model, some of the ways to remedy it, and then more broadly speaking, how to build tooling and infrastructure around that. So to get started, a lot of the work that I'm going to be talking about today was actually born out of a research paper from several years ago called ZK8. It was published in Oakland 2020 and introduced a protocol that extended the zero cache protocol, or aka Zcash, to support general purpose applications. Before I do jump into things, though, I think that it's worthwhile, especially because there's a lot of newcomers into this space, to really go through how zero knowledge at a very basic level works. And before I even do that, I want to thank Anna for putting together this amazing community. It's been several years in the making, and the good news is, because not many people clapped for ZK1 when she was checking, I can reuse a few slides in here, which will be also very helpful, since I want to make sure everyone's on the same page about how zero knowledge works, what the concept of zero knowledge proofs is, and fundamentally, what are the assumptions, the trust assumptions between the prover and the verifier, which we'll talk about next. So let's jump right into things. In terms of the talk today, the content's going to be broken into three parts. The main thing that I really want to convey is that there are things called ZK snarks. My hope is to help you understand on a higher level how things work there, and then dive into the concept of a ZKL1 and how you can build a virtual machine around a blockchain that can be provably verifiable. And then lastly, to get a little snarky and talk a little about the way that we're instantiating things on Aleo. So let's jump into it. What are ZK snarks? Well, to even talk about that, we need to start with a basic premise, which is to say that cryptography is a really powerful tool for building secure systems. And much of the cryptography that we use today is really to give security guarantees about data. What do I mean by that? Well, for one, whenever you're transmitting information, say over the web between two parties, one of the things that you really want to do is to encrypt your content so that only you as the sender and the receiver see this message. And so we use cryptography for encryption. The second way that it's commonly used today is really to offer security properties with respect to authentication. And what I mean by that is that when you have the sender and receiver communicating with each other over the web, you want to make sure that the receiver is really getting the message from the sender. And so, one way that you can do that is you sign the message and then send it over. And these are the two primary mechanisms that we use cryptography for. It's really about securing data, and data at rest, really. But the question is, can I use this type of cryptography to do even further, to really give guarantees about computation? And this is where the domain of cryptographic proofs comes into play. Cryptographic proofs can offer privacy-preserving guarantees for computation. And that's something that's, in my opinion, a very new field, a very new domain in terms of what's becoming practical and ready to use in the real world. In particular, a cryptographic proof is really saying, hey, I securely computed this equation f of x, and its result was y. And the goal is to convince other parties on the internet that I really did do this. And when you dive in and double-click, there's an even further kind of specific segment of cryptographic proofs called zero-knowledge proofs. And zero-knowledge proofs are there's a lot of jargon here, so let's break it down. The privacy-preserving cryptographic proofs of computational integrity. And this is really taking it one step further. And what I'm really saying here is to say, I know x such that y equals f of x, where x itself is a private input. And this takes that concept of a cryptographic proof and kind of takes it one step further. So when you're on the web, sometimes you don't want to share everything that you have or know, especially when it comes to personal information, PII, across the web to other people as well. But in order for other people to verify that you really ran this program and got this result Y, they need to somehow trust or believe that you used the right inputs. And if you don't want to reveal that, then zero-knowledge proof ends up becoming a very useful primitive for this. I think another way to frame a zero-knowledge proof is to say in English that I know the secret, I can't tell you the secret, but I can prove to you that I know the secret. And this is really getting at the heart of what zero-knowledge proofs are about. It's really trying to convey information to another party without revealing the full set of information that you want to reveal. So to give you a concrete example of it, there is a very canonical example that many of you may have seen on the internet, which is the where's Waldo problem. And it says, the question goes like this: can you prove to me that you found Waldo without telling me where he is on the map? And you can take a moment to think about it. I'll give a quick fun anecdote, which is to say that when in creating these slides, I actually had to go find an image of where's Waldo. And it took me quite a while on Google search to find a good image of this, because I had to keep checking whether the image itself had Waldo in it. I wasn't sure if there would be an April Fool's prank in there or not. So it would have been really nice if there was already a zero-knowledge proof for it with the image so that I could just pick one that looks really visually nice. But just to give the answer away, first off, Waldo's like right there. And the way that you want to show to another party that you found Waldo is really as follows. You want to take a really big white sheet of paper and cover the entire screen with it. Just the entire screen, something that's just much larger than the map itself. And you want to cut a little hole in that white piece of paper, just enough to fit the size of Waldo, so that when another person comes into the room and just sees a giant blank canvas with a little hole and sees Waldo sticking out, they can be really convinced that there is Waldo on a map and Waldo truly exists, and that you found Waldo. Then, if you ask them to leave the room and you remove the white canvas, when they come back into the room, they just see the basic map again, and they can now take a stab at it. And that's one way to kind of convince you that, I really found Waldo. Waldo exists on the map, and I know where Waldo is on the map, but without revealing where Waldo is relatively on the map. Where is Waldo? He's right there. So yeah, this is one canonical example, and I'll very quickly run through just another one, which is the Alibaba Cave, which is also a classical one. If you go to the Wikipedia page, you'll find this one, and credits to Wikipedia for the images too. But just to give you some background context, this example actually came from a paper back in 1989 called How to Explain Zero-Knowledge Protocols to Your Children. I'm not sure whose children are learning about zero-knowledge proofs, but for them, I say I applaud you, and I'm very excited to work with you in the future. You guys are going to be geniuses. But the basic premise goes like this. You have Alice and Bob. Alice is basically walking into a cave. The cave has two sides, branch A and branch B. Both branches are actually connected by a door on the back side there. That's that black line. And once Alice walks in, Bob can flip a coin and say, I want you to come out of, say, A if it's heads or B if it's tails. And if Alice has the key, Alice should be able to walk right through that door in order to come out the appropriate side. So if Alice randomly said, I'm going to go in path B, and Bob says, come out of path A, well, she should be able to open that door and walk right through if she has the key. Now, as you can imagine, there are also, quote-unquote flukes where you could say, Alice walked in B, Bob flipped a coin, the coins had come out of B, and then Alice comes out of B without the key. And this is why this is more probabilistic. You want to play multiple rounds of this game. If you play multiple rounds of this game, probabilistically, you can bound the chance that she's really lying to you down to eventually zero. The limit goes to zero. And this is a very canonical way of kind of explaining how the zero-knowledge protocol really works, because most of the schemes, especially in the early days, were designed around interactivity and having this kind of prover-verifier challenge, as it's commonly called. But so yeah, let's dive right into things. So the first zero-knowledge proof was actually invented in 1989. It's by Goldwasser, McCallie, and Rakoff. And back then, the model was basically this. You had a prover that had a function f, some claimed output y, and a private input x. You also had a verifier who knew the same function and the same claimed output. And the goal was to say, the prover says, I know some private input such that y equals f of x. And the verifier says, prove to me that you know x. And what they would do is they do this multi-round interaction and communication. So the verifier would effectively send challenges over to the prover. The prover would evaluate those challenges, send responses back to the verifier, and do this several times. And similar to that Alibaba Cave example, if you did enough rounds of this, the probability bounds got you to the point where you could feel confident that, well, the verifier would be convinced that the prover must have the secret. If the prover doesn't have the secret, they couldn't answer all of these queries in a go. And so that was the way that this was designed. But This, as you can imagine, from 1989, had a lot of trade-offs. First off, as you can see, it was interactive, and if you imagine that this is on the internet and you have two random strangers on the internet, asking both of these strangers to be online on the internet at the same time to communicate is a pretty big ask, and interactivity foundationally is therefore a challenge. The second main thing is that, well, this design itself was not succinct, and what that means is that the actual proof itself to verify took roughly as long as it would take to compute the function f itself. And so if you wanted to, say, outsource some work to another party and have them compute it for you, well, to check that they did the work correctly, you'd basically take as long as it would take for them to actually produce the proof, and that's not a great guarantee as well. And the last thing was to say that it had very poor concrete efficiency. So the prover took a really, really, really long time to generate the proofs for you, and therefore this was really impractical from a real-world context. It was incredible though from a pure academic and theoretical construct to say that you can use math to even make claims like this. So in order to remedy some of the issues I just talked about, actually in 1994, Silvio Micali published a paper that showed the first succinct non-interactive ZKP. And the idea there, again, was to say that there was a prover, but now the verifier was actually really, really small. And so that's the succinct property. And diagrammatically, I show that the verifier, therefore, is much smaller. And the prover actually made the same claim as before. It says, hey, I know some x such that y equals f of x. And the verifier once again said, prove to me that you know x. And now, instead of doing multiple rounds of interaction, they use basically a random oracle. You can think about it like SHA-256 or Poseidon in this case, as we now use today. But the premise was that instead of having to have the verifier come up with some random challenges that then get sent to the prover, who then evaluated it, who sent them back to the verifier, who then sampled some new challenges and sent them back to the prover to send more responses, they could both agree on, for example, a hash function and say, hey, like, here's the pre-image we're going to start with. If we both agree on this, we can then hash from here and use the same assumptions for what you should be evaluating. And then, therefore, the verifier can just say, well, I knew what you were starting with, and I could iteratively check that you actually use the same call functions to do the actual interaction part normally. And this saved on the actual need for both parties to communicate with each other. The end result is that the prover only had to send over one proof to the verifier. This ended up being a non-interactive scheme because of that. And this was actually the first ZK Snark. And so it's been, like 20, 30 years since we've gotten from the original concept of a zero-knowledge proof to where we are today. But there has been a number of things that have, a number of advancements, especially in the theory and the engineering, that has gotten us to a point where we can now run this stuff in the wild, in the real world, on very expressive statements. But before we start talking about that part, I don't know how many people are familiar with ZK Snarks in its entirety, and so I want to just give a quick definitional construct for it. So zero-knowledge proof itself, basically, ZK Snark stands for a zero-knowledge, succinct, non-interactive argument of knowledge. That's a lot of jargon. What does it mean? Well, zero-knowledge means that the proof doesn't reveal the witness. The witness is commonly the private input in this case. That's the secret that you don't want to reveal. Succinct just means that the proofs are small, so they're like, a kilobyte or less. And the verification is fast, which means it's like, 10 milliseconds, 20 milliseconds, something that's realistically practical and fast to check in your browser. The third is that it's non-interactive, which just means that there's no interaction that's needed between the prover and the verifier. And lastly, it's an argument, which just means that soundness holds against a polynomially bounded verifier. This is a more technical delineation because there are statistical bounds and there are computational bounds that one can give for the verifier here. And so this is one set of that. So hopefully that gives you some context into what ZK Snarks are. And now I want to talk a little bit about how you can use ZK Snarks to basically build a layer 1 programming model around it. I think the easiest point to start from, frankly, is the account model, because I think everyone here, or almost everyone here, has had some interaction with Ethereum before. So before we jump into things, I think it's well motivated to say that people really like to build applications in Web3, and there's many use cases for it. And the goal is to say, can we build a ZKL1 that can support every one of these? Yes, the short is you can, but it comes with a lot of limitations. The first is that, well, When building a decentralized ledger, we need to operate by verifying and confirming that each transaction works via re-execution. What do I mean by that? You have a user who's submitting a transaction, and it's composed of the application, the input, and the signature. And the user broadcasts this transaction to the network, as so. And each node on the network then re-executes the associated computation in that transaction. If the computation is correct and the signature is valid, well, the application gets updated. And as you can already begin to see, there's a lot of re-execution that's going on in this model. And so let me walk you through some of the limitations of this. First, it's that ledger re-executions really hurts scalability. So in general, every transaction rerunning computations on every node on the network will result in a lot of wasted work. In fact, if you just take the Ethereum structure from ETH1, and I realize that post-merge we got to redo the numbers here. This is 3,000 nodes. If we just assume that there's like 5 seconds of computations in each block, and this math already adds up to 15,000 seconds, or about 4 hours of re-execution. That's a lot of wasted work. And you can naturally see just from the previous slides on what a ZK Snark is you probably want to try to, kind of give a proof about it so you don't have to recompute it and everyone doesn't have to recompute it. That's like a big deal because this model here is, well, wasteful. The second thing is that ledger re-execution hurts privacy. And what I mean by that is that like in the existing models of decentralized applications, you learn everything. You learn who's the caller. You learn who's the receiver. You learn what program you're calling. And you learn the logic of the program as well as its data. And like this is something that I think requires a lot more nuance if we're going to take this out into the web. The classical example that I give is to say, if I want to send you money and you give me your bank account number, knowing your bank account number reveals nothing to me about how much money you have, how much money you make, how much money you spend, where you spend it, when you spent it. So it doesn't reveal to me any of these things. But if you give me your Ethereum address, now I know all of these things about you, and I can track you also for the rest of time with that. And so this is fundamentally just a UI UX challenge that Web3 introduces that we need to kind of think about if we want to take this technology out into the real world. And so we built something called Aleo. Aleo stands for Autonomous Ledger Executions Off-Chain. Aleo itself is a decentralized ledger and enables users to execute programs off-chain and finalize state on-chain. The ledger provides several properties. The first is that we achieve scalability, meaning thousands of transactions per block. The second is that we preserve privacy, meaning the resulting transaction reveals no information about off-chain computations. And lastly, we have succinctness, which just means that the resulting transactions are small in size and fast to verify. Concretely, for reasonable parameter sizes, we get transactions that are approximately 1 kilobyte in size, and they can verify in less than 50 milliseconds. And so our programs also provide us with several properties. The first is, in terms of functionality, we enable arbitrary user-defined programs. And while isolating malicious programs from honest ones, and we enable program functions to communicate with one another in a secure manner. So to see how we arrived at this design, let's start by analyzing this popular framework called the account model. So in the account model, you basically have a decentralized ledger that's tracking global state. And to perform a state transition, the user usually signs an input, a transaction, that produces a request to say, hey, please execute this program with the given input fields. And once the transaction's been verified, well, it's confirmed into the next block by the ledger, and the account state updates itself automatically. It's an internal operation, and it transitions from the previous state into the new state of the program. The intuition here is that users invoke programs with these inputs via transactions, and the ledger updates that internal state based on the outcome of that transaction. Naturally, one of the biggest benefits of the account model, as you guys know, is simplicity. It's really easy for developers to coordinate and manage state between multiple parties. But there's a few trade-offs, of course. One is that there's kind of a scaling problem. There's also a high fee problem, and they're duals of each other in the sense that complex tasks can be time-consuming, and large queues of unconfirmed transactions can build, which causes significant spikes in the network fees to occur. And the last one, naturally, is that there's just no privacy in the account model today. And what do I mean by that? Well, transactions reveal the contents to everyone on the network. Means the sender, the receiver, the program inputs, outputs, and state are all publicly known. So what do we want to do? We want to redesign this ledger, and we want to minimize the re-execution and maximize privacy. And so how do we do it? Well, let's just sprinkle some ZK snarks on it, of course. We want to extend the account model and see where we land here. So let's take a first attempt at extending this. And the intuition is to say, let's start with private smart contracts. Instead of revealing in the transaction your value, the data, the call data, and the signature, why don't we move things over into saying, let's commit to the values, let's encrypt the data, and instead of using a signature, let's start using cryptographic proofs, as we talked about. And for on-chain state, with your account, instead of publicly showing your balance and publicly showing your code and publicly showing your storage, why don't we commit to the balance? Why don't we create a predicate about your code, and why don't we encrypt your storage? Then from here we could say, now when a user is creating a transaction, they're really revealing a transaction that has very little publicly reasonable data. And what's being updated on chain is not the actual data itself, but commitments and encrypted data from the previous state into the new state. That's the rough intuition on doing this. Now, if it were this simple, I don't think I would need to be here talking about this design. So let's start thinking through some of the properties here in this design. Why this doesn't work? Well, for one, concurrency is a really big problem. Let's say you have user A who wants to make an update. So he calls with transaction 1, update program A. If party B comes and says, I also want to update it in the second transaction, this actually doesn't work. Because the entire state is now encrypted, only one party at a time can actually go and update that state, because you have to Merkleize things in a cryptographic system, and your root is effectively expiring as you're making that state transition. The second issue is that we still don't have full privacy in this account model. Why? Because everyone can see that user 1 updated program A. And the reason for that is, if we go back just a few slides here, the transaction still reveals the address, not only the address of the user, but the contract address that you're referring to. And so if I were in that bank account model saying, I want to send money to you, give me your address, I might not know anymore how much you're spending or how much you're doing, but I clearly can see you're using this account, and I can see which applications you're using, and I can still cluster and deduce how frequently you're transacting and where you're transacting. You can also still figure out who's paying you for your salary, and also who's paying you in general to say pay back debts or pay back loans. And this then therefore says this is not full privacy, at least in the canonical definition. So let's analyze the properties more concretely. The first is to say, we have no more ledger re-executions. Why? We use a zero-knowledge proof, and with the zero-knowledge proof, we're able to achieve scalability and succinctness. The second thing is that we achieve data privacy. As we said, there's no account privacy, but we do have data privacy because we're using commitments and encryption to hide program state itself. But as we just said, the address can't be encrypted because in the account model, you're indexing by address. And so as part of that, the ledger fundamentally relies on it to index into global state. Fourthly, we have a lack of efficient state updates. Why? As we just said, we have to consume the entire program in order to make one state transition about it. That's not a great model. Like, imagine if you want to update your UC20 and you have to reason about every other person's account as well in order to make one cryptographic update. And lastly, of course, there's no concurrency, because when one person makes the full update, you invalidate the ability for another person to update the same state at the same time. So the proposal that we came up with was to say, let's introduce something called the record model. What is the record model? Well, in the record model, the decentralized ledger still tracks, or now tracks, the records of each account in global state. And to perform a state transition, users generate a transaction computing a zero-knowledge proof that attests to the state transitions for the given execution. Once the transaction has been verified and confirmed into the next block of the ledger, the program updates itself internally. And this transitions that previous state into the new state of the program. The intuition here is that the users only consume the records that are necessary to make the state transition that they want for their program in their context. And this no longer requires you to consume that entire state. So because of that, you actually get concurrency, because I'm only reasoning over the records in the account that belong to me. And then I'm going to take those records and produce a state transition out of it. The second thing is that this also enforces double spend conditions. Why? Because your account state is now properly indexed using records, if I'm going to try to spend this record twice, it can be easily detected on the network that this record was previously spent, and I can't re-spend this record again. And this model then gives you some way for consensus to easily check cryptographically that indeed this state was only used once without actually seeing the contents of the record. So when we come back to it, now that we have abstracted into a record model, we actually get account privacy. Why? Because the decentralized ledger indexes global state based on these program IDs. These IDs end up becoming the actual clustering point as opposed to your account address. And that fundamentally changes the assumptions that are being made in the privacy model of programming. We also get very efficient state updates because you only need to consume the records in a program that belong to you or the ones that you actually want to use in order to perform the state transition. And lastly, you can also do simultaneous updates because within a program, you now have this record system which says that you only need to consume the records which belong to you in order to perform your updates. And other people can touch their records to perform their updates. And this type of isolation is what enables multiple parties to interface on the same application at the same time. So hopefully that helps give you some color into how you design the record model in this context. And lastly, I want to just say, like, we want to instantiate this. So how are we going to instantiate it? Well, in order to instantiate it, we have to use a lot of technology, a lot of disciplines in order to come together and build this thing. And Aleo is at the intersection of several different disciplines. Everything from everything from mathematics to complexity theory to cryptography, computer security, and programming languages. We sampled curves that enable Snark-friendly cryptographic primitives. And namely, we sampled a 377-bit curve with embedding degree 12, which we call BLS12377. This curve is great because it supports fast proof verifications in our construction. We also sampled a twisted Edwards curve, and it's useful for efficient Peterson hashes and commitments, as well as signatures. And in general, Edwards BLS12 enables efficient circuit operations. Finally, we instantiate our Snark. Our Snark here is Marlin. Marlin itself was published at Eurocrypt 2020, and Marlin's great because it requires only a single trusted setup for all programs. This is the universal setup that Alex previously was talking about. If you'd like to see our work, the good news is it is open source. The work here that we have is with respect to Leo, Aleo, and the AVM itself are all on GitHub. And the rationale is to say I can take a very high-level piece of language called Leo, a piece of code in Leo, compile it down into an assembly-like language called Aleo instructions, and from there serialize this into AVM bytecode, which then can be deployed on-chain. So earlier when you saw with the programs and records on there, the program itself contains a predicate that's represented with respect to that AVM bytecode, and all of the code prior to that is from off-chain, from the developer themselves, writing out exactly how the two parties should be interacting. To give you just a small taste of what this looks like, this is the syntax for Aleo instructions. You can see here function main, and my inputs start off with registers, register 0 and register 1. In this example, what I want to do is multiply these two numbers. So I can pass in a public field element and a private field element. I can multiply these two things into register 2. And then lastly, I can output as a private register the field.private, basically, the result of that multiplication. Because this is adhering to the account model, what this actually does is say, when I want to broadcast on-chain the private state, I need to encrypt this, and this will get encrypted under my account address. And so only I, using my account, can go on-chain and see the result of this computation with my view key. This is the difference between existing programming models in kind of EVM-based systems and the new set of ZKL1s that I believe will use a model similar to this. Lastly, I want to say thank you. Aleo is proudly written in Rust. We have written a ton of lines of code. We probably need to do some refactoring, but there's been a wonderful community of 40+ contributors who are building on us and helping to make Aleo happen. We are available at this URL, github.com/AleoHQ. And lastly, testnet 3 is live, and for those who are interested to play with our network, the developer docs are available at developer.aleo.org. And with that, I want to thank you for your time and attention, and hope you have a wonderful day. Thanks.